Okay kids, we will be continuing it, so you can look into the passage. A straight conductor AB of negligible resistance and mass m is placed on the rails of negligible resistance as shown. Distance between both the rails is L and leftmost ends of both the rails are shorted with the help of capacitor. The conductor is joined to a non-conducting ideal spring of spring constant K, which is fixed to rigid support. The whole system is placed in static magnetic field, which is directed into the plane of the paper. Now the conductor is shifted to the right by distance x0 to compress the spring, and if you leave it, then what will happen? The least time for which the conductor, so there is no energy loss anywhere, there is no resistor, right? So when you push it and when you leave it, it will be coming this way. While it is coming this way, then V bar cross V bar, there will be induced EMF which will be charging the capacitor. Sorry, V bar, again I am making a mistake. So V bar cross V bar, it will be charging the capacitor, right? So that's the idea. Anyway, we'll see. So this is what is happening when you compress it by distance x0, and when you leave it, it will be coming this way with some velocity. When it is coming with some velocity, V bar cross V bar, it will be driving the current this way. If it is driving the current this way, then okay, L bar cross V bar, that force will be in this direction. Now spring force is in this direction and magnetic force is in this direction. I am taking net force is in this direction because it will be a such thing anyway, right? So from the mean position, when it is at a distance x, I am going to write the force equation. So right now potential difference here and here should be same. So charge here will be C into potential difference, that is BLV. BLV is the potential difference, right? Now similarly, net force equals to mass times of acceleration. If I write, spring force is K into X and magnetic force is L bar cross V bar, I into L into B in this direction. So net force is in this direction equals to mass times of acceleration. Now what I did, I assumed the directions already. Now what does this say? X is in this direction, V is in this direction, A is in this direction. So V is nothing but negative of X dash, negative of X dash, right? Both are in the opposite direction. But A is nothing but V dash, A is nothing but V dash, V dash is nothing but negative of X double dash. If you differentiate this one, you will be getting negative of X double dash. That's mathematical thing anyway. Now we need to show it is SHM generally. So what we will be doing, I need to find I. So I am differentiating this, I am finding I. I am finding I, Q dQ by dt is I. So I am substituting this I back, this I back. So yeah, I am taking it here. dV by dt is V dash. So when I take it here, I will be getting m plus C B square L square into, yeah, m plus C B square L square into V dash. Now what is V dash? Minus X double dash. V dash is nothing but minus X double dash. You can see it is SHM form, you can get the time period. Now at the mean position, speed is going to become maximum, or natural length will happen. So at the mean position, that is when you push it to the extreme, after t by 4 time it will be coming here. Total time is this much. So t by 4 will give you answer for the first question. T by 4 will give you answer for the first question. Now maximum speed of the conductor. Maximum speed of the conductor, you got omega value from here. This is omega square, right? So amplitude into omega will give you velocity. That way you can get option A easily, quickly. Or okay, I didn't do that. What I did energy conservation. Energy stored in the capacitor plus kinetic energy plus potential in the spring at any time should be constant, which is equals to initial potential energy in the spring. Now maximum speed, when maximum speed is happening, there will be EMF. So when there is potential difference, there will be charge also, or Q is related to V, which we have already seen. If velocity is maximum, charge will be maximum. So if velocity is maximum, charge is maximum. So if this is maximum, this is also maximum, then this has to be minimum. This minimum is 0. So charge we have already found as a function of velocity. When you substitute, you will be getting maximum velocity. Once you get maximum velocity, you can substitute it back to get what is the maximum charge. You can substitute it back to get what is the maximum charge. A uniform magnetic field B exists perpendicular to the plane of the figure and circular region of radius B is its center O. A uniform cross-sectional circular conductor of radius A, which is less than B, center at O, is made by joining two circular segments ABC and ADC. The magnetic induction field strength varies, okay, it is reducing, so magnetic field is reducing, so then the induced EMF will be in this direction. So if it is made of same material, then the induced EMF will be trying to drive the current, but here it is of different material, so still when steady state is achieved, currents in both the things should be same, but this resistance is more than this resistance, so more electric field should be driving the current, right? Because J equals to sigma A. If steady current is happening, J should be magnitude wise same at every point. If J is same at every point, then electric field has to be more. So, but we know induced electric field will be same everywhere, and we can get that by using rate of change of flux thing. So, induced electric field will be same everywhere, but total electric field has to be more. If not more, then what will happen? Then current in this one will be less, current in this one will be more. It is not a steady state. So when current in this one is more and current in this one is less, there will be charge accumulation happening. Now because of charge accumulation, what will happen? Electrostatic field will come into picture. I will be showing the figure. So this is what happens. Induced magnetic flux is decreasing. If the magnetic flux is decreasing, induced EMF will try to drive the current this way. If the induced EMF is trying to drive the current this way, current in this one will be more and current in this one will be less. So what will happen? There will be accumulation of charges happening here. Because of this, not only on this, there will be surface also. On the surface also there will be accumulation of charges, which doesn't matter much. So there will be electrostatic field developed, which will be pushing the charges further. There will be electrostatic field developed, which will be reducing the speed, such that it can increase the speed here and it can reduce the speed here, such that it can maintain a steady current. This is the idea. Now induced electric field you can get using rate of change of flux magnitude wise. Now option C, I made it correct. The induced electric field is uniform everywhere in the circular loop. This induced electric field is same at every point. Yes, that is true. Now if I take first material, then J bar equals to sigma into E bar. See, J bar should be, okay, magnitude wise it has to be same. Okay, anyway, J bar equals to J1 bar equals to sigma 1 bar into E1 bar. So you know sigma is same everywhere here. So and current is also same in steady state. Current is this way. So current is same and sigma is same. So total electric field has to be same. This is total electric field. That is the combination of induced electric field and electrostatic field. This combination of induced electric field and total induced electric field and electrostatic field. Now I can modify it. I can multiply magnitude wise. I can multiply with rho L by A and stuff. Yeah, J into A will be current, right? J into A will be current. I can do I into R equals to, yeah, I mean this I can bring it here. It will become rho and I can multiply and I will be getting I into R is like integral E bar dot dl bar. Integral E bar dot dl bar. E is same everywhere magnitude wise, so it will be E1 into, now this length is pi into A. Now what is this electric field? This is the total electric field, that is induced electric field plus electrostatic field. Induced electric field, now see, that's not the electric field, that's the EMF. Okay. EMF. So in this electric field consists of induced electric field and electrostatic field. Induced electric field into pi A will give us EMF, that EMF because of induced electric field. For the full loop it is E, so for half loop it is E by 2. See, induced EMF in the full loop is E, so for half loop it will be E by 2, for quarter loop it will be E by 4. So when I do that, this I have written in a direct step, this consists of two parts. So first electric field into pi into A will give me E by 2, second electric field, which is electrostatic field, into pi into A will be giving me the second term. Now both are in the opposite direction, so I have written minus here. Now similarly, if you take the other case, there they are supporting in nature, so you will be getting E by 2 plus E into pi A. Now what is this? This is induced electric field times this length, that is induced EMF in this part, right? So from there I have marked C is correct. C we have already marked, it is correct, right? B, magnitude of net electric field is different in semicircular wires. Yes, sigma is different J value is same magnitude wise. Magnitude wise J value is same, but sigma value is different, so net electric field value is different. Yes, B is correct. Then going to option A, magnitude of current density. Okay, magnitude of current density is same in both the wires because steady state will be achieved. Till then the charges will be like accumulating and it will happen very quickly. Now the magnitude of static electric field, that is electrostatic field, so we need to find E. So how to find E? We can subtract these two, or so what I did, I added these two to find E as a function of IR. I subtracted these two to find this E as a function of IR, and yeah, I'll be taking the ratio, or I can eliminate this IR, right? IR is E by 1 plus eta. Now what is E? That E we have already found, induced EMF. Induced EMF. Right, you can substitute the values and get the answer. So what is the core idea here? The core idea is induced EMF will try to drive the current this way, but because of the different resistivities, steady state current won't be there. Because of that, charges will start accumulating. Now these charges will accumulate very quickly and they will produce some electric field which supports either ways the steady current. So it will increase the current in this direction and it will reduce the current in this direction such that steady current is maintained. So that's the idea, and J bar equals to sigma times of E bar is valid everywhere, where E is the net electric field. Net electric field which consists of both conservative as well as non-conservative. So I think going to the next question. Yeah, next question, option A is wrong according to me because current density is a vector quantity, its direction is changing. Magnitude wise it is same, and drift velocity of the electrons, sigma is depending on, sigma equals to n E square tau by m. So E is charge of electron and m is mass of electron, and so it depends proportional to n and tau. So I don't think I can conclude anything there. N into tau is constant. Oh, sorry. Sigma is n E square by m into tau. Sigma. Drift velocity is E by m into electric field into tau. So electric field, drift velocity is proportional to electric field and tau. So I can't conclude anything there. So if I assume tau is same, so time of collision is same, relaxation time is same, then it depends on the net electric field there. So net electric field is different, so it will be different. Yeah, so then I will go with it is different. At junctions A and C there will be accumulation of static charge. Yes, that is the reason you will be getting field. And J equals to sigma is valid because steady state current, both J's should be same magnitude wise. So sigma 1 E1 equals to sigma 2 E2, where E1 and E2 are net electric fields, right? This question we have already discussed in, I have already taken it in multi-correct I think, but again, so those who didn't watch it there probably you can see. Parabola will happen when electric field and velocity will be making some angle. Circle will happen when velocity and magnetic field are perpendicular. Straight line will happen in many ways, we will come to straight line later. Cycloid will happen when electric field and magnetic field are perpendicular to each other and a particle is released. Helix will happen when velocity is making some angle with magnetic field, or that is with constant pitch. If electric field is also along magnetic field direction, then it will be forming helix with increasing pitch. Now straight line will happen when nothing is there, or when magnetic field is along the same direction as, along the same line as velocity, or electric field is along the same line as velocity, or there can be another chance where net force because of electric field and magnetic field will become 0, right? Now for all these questions you should find current through the inductor and current through the battery. Options were given wrong, I will be just finding the values, so you just go with that. So in this case I can find equivalent inductance, so 3 and 3 6, 6 and 6 3, equivalent inductance in 6 3, so time constant is L by R. Once I know time constant, then I can find current through the battery. Current through the battery is maximum current 1 by 10 into 1 minus e power minus t by tau. Once I know current through the battery, current through the inductor will be half of that, it will split into two parts. Now either you write this loop equation or this loop equation. So these two looks like different equations, so I can find for any one guy. So for this guy, current, when I write the loop equation, maximum current in this case is going to be half ampere. So half into 1 minus e power minus t by tau. For this guy, what is tau? L by R. So in this guy, whatever is the current, in this guy also the current will be same. So this current will be 2 times of that. In the next case, again, when I write this loop equation, whatever, let me say this current is I1, this current is I2. If I write this loop equation, I2 will never come into picture. If I write this loop equation, I1 will never come into picture. So I don't have to bother about this guy, I can take this loop separately. If this is the loop, if I write the loop equation, I can get the time constant as this L by this R. Or those who are familiar with Thevenin's, you can make into Thevenin's anyway. That will show you Thevenin's resistance is 10 and Thevenin's voltage is 10. So now what is the maximum current in this? 1 ampere. So I equals to 1 into 1 minus e power minus t by tau, where tau value is this much. Now current in this one is always 1 ampere. Current in this one is always 1 ampere. Current in this one is this much, right? So current in battery is going to be current in this one plus current in this one, which is this plus 1 ampere. Now in the next case, it is Wheatstone bridge. So no current will be flowing through this. Current through the battery equivalent resistance is 2 and 2, 4, 4 and 4, you will be getting 2, so current will be 1. So current in the inductor is always 0 and current in the battery is 1, right? Thank you.